Hello. In this module, we will learn how to use Bode plots for meeting our design purposes. So, we will call it as design in the frequency domain. So far what we have done in the previous module was to learn how to design compensators, and our main analysis tool there was the root locus plot. So, we had the issue of uh, addressing transient performance specifications via a lead compensator, addressing steady state performance specifications via a lag compensator, and in cases where neither of these are met in the open loop, we go to design a lead lag compensator. And so, here we will see it from a slightly different perspective, from the perspective of the frequency domain. So, as we saw that the lead compensator was used to improve the transient response, lag was for the steady state, and in case we wanted to improve both, we use the lead lag compensator. So, here the tool which we used was the root locus, and now in the frequency domain design techniques we will make use of the Bode plots to verify our design or even for the analysis purpose. Okay. So, let us quickly again recollect what was the root locus based approach to design. So, the transient requirements were given to me in terms of the peak overshoot, in terms of percentage, and I had the settling time, and these two specifications were translated to the location of the dominant pulse, and the root locus was used in such a way that I would want the root locus of the compensated system to pass through the dominant pulse, right. And then in the final design we ensure that the dominance conditions are met very closely. We may not really get an exact overlap between the dominant poles and the compensated plant, but we know techniques of how to get them as close to each other as possible. Okay. So, what will we do, or what will be our philosophy in the frequency domain techniques? So, in this case the transient requirements are specified in terms of the phase margin, the grain crossover frequency, sometimes the resonant peak, and even quantities like the bandwidth. So, what we saw while we were analyzing the frequency domain plots or the frequency domain response was that there is some relation between the specifications in the frequency domain and the specifications in the time domain. We will again recollect those. So, in this case the design would involve reshaping of the Bode plot to meet the specifications. So, as analogous to what was happening in the time domain, that we wanted the root locus to go through or pass through the dominant pole location, similar specifications will have to be met even in the frequency domain via the Bode plot, and we will see how we do that. And this also advantageous to me in more than one ways, right. In cases where the model of the system is not available, and in cases where I could get or I could construct the open loop frequency response, this method is extremely helpful. So, in a way it means that I could actually construct the transfer function by just seeing the response of the system for various frequency signals. Once I could construct the transfer function, I will have a model of it, and from the model I can go to design the frequency domain compensator. So, this is a part which we will do in the next module, which will be titled experimental determination of the Bode plot. So, given a frequency response or given a Bode plot, how do I obtain the transfer function? That we will do in the next module, but at the moment it's safe to assume that if I do not have a model, I can actually construct a model by using the frequency response techniques. Okay. So, again just a very quick recap. So, a standard second order plant in closed loop looks like this, where you have the damping coefficient, the natural frequency, typical step response for an underdamped case looks something like this, where the overshoot was calculated as a function of the zeta, settling time depended on both zeta and omega n, and similarly we had other quantities like the rise time. Right. And in addition to these three specifications, we also had the steady state specification in terms of the position error, the velocity error and the acceleration error, or the error constant, so to speak. Okay. The closed loop characteristics have few components. So, first is, so if you see, this is the response to different frequencies. So, I will start from here, we will have a peak and again go down, right. So, this we earlier termed it as the resonant peak, and the frequency at which this occurs is the resonant frequency, and we computed that this was directly depending on the damping factor, and the resonant frequency was depending on the damping factor and also the natural frequency. Similarly, for the bandwidth, right. So, bandwidth was computed in the following way, that it is depending on omega n and also the zeta. Okay, so what is the observation from these three things? That systems which have large bandwidth or bandwidth close to n, which means zeta would be close to 0, bandwidth close to omega n, which means the zeta would be closer to 0, and the smaller the zeta would mean you will have a smaller rise time and so on. Of course, you will have to trade off in terms of the overshoots. However, I would, from the filtering perspective, my noise signals appear as high frequency signals, and I would want to filter them out as much as possible. Therefore, just by merely increasing the bandwidth or designing my system to have a very large bandwidth is sometimes not desirable, and therefore we need to have a trade off between the bandwidth and the rise time or even the overshoot. Okay. Okay, now a little bit more on the specification. So, MR, the response of the frequency or the resonant peak here, depends only on zeta. Therefore, and if you look at even the formula for MP in the time domain, it also depended only on zeta, and therefore we can say there is actually a very nice correlation between MR and MP, right. Therefore, given a specification on MR, I can directly have translated into a specification on MP or specification on zeta, right. So, in the same way as peak overshoot, the resonant frequency is also an indicator of the relative stability of the system. Okay, so the expression for the resonant peak tells me that it exists only for these values of zeta, and therefore the correlation between MP and MR exists only for zeta between 0 and 1 over square root of 2, and is given by the plots like this here, right. So, at zeta equal to 0.02, I have 0.707, I have this number, that MP goes to closer to 1, right, which you can get from this expression. Okay, so what happens for zeta which is larger than this value? Well, for zeta larger than square root zeta larger than 1 over square root 2, the peak overshoot is very insignificant, right, if you just compute it from the formula for the MP. And therefore, I do not really need to worry about what happens for larger values of zeta, because the overshoot is very minimal. Okay. Now, for a given zeta, right, either omega n, or the bandwidth or the resonant frequency can be used to specify omega n, right, which is apparent from these three formulas. Okay. And therefore, you can say that the bandwidth and the resonant frequency, they influence the rise time in the step response, again just by these three formulas and relating it to the formulas in the time domain. You write the rise time as zeta and omega n. Okay. And therefore, we can conclude that larger the bandwidth or omega r, which we also argued here, larger the bandwidth or the resonant frequency, smaller is the rise time. Okay. Now, further, how do we translate performance specifications from the time domain to the frequency domain, or are there any direct correlations? So, let's see with the help of the plots here. So, the expression for the gain crossover frequency is depending on omega n and zeta, and similarly the phase margin has a direct relation with zeta given by this formula, right. And moreover, a standard second order system this system is always stable, right? It has an infinite gain margin and the phase margin is always a positive constant, right. So, as it is obvious now that the phase margin depends only on zeta at this one, and defining the zeta has a direct correlation with the peak overshoot in the time domain. Therefore, specifications on the peak overshoot directly translate to specifications on the phase margin of the system, right, through this expression. Okay. Now, again, larger the damping ratio, larger is the phase margin, and therefore the system is relatively more stable. Larger the damping ratio, more the poles shift to the left in the root locus or in the time domain, and therefore we can say the system is more stable, right. Okay. Now, if we look at the plot of zeta versus gamma, the phase margin, which is essentially a graph of this function, what we see is that for lower values of zeta between 0 and 0.5, I can get this linear relationship that zeta is gamma over 100, and this is a very close approximation if you just look at this plot. Okay. This actually means that if I design want a phase margin of 45 degrees, it approximately means that I am looking at a damping ratio of 0.45. And for a given phase margin, I can always relate it to the gain crossover frequency and the bandwidth. Again, we just go through the expressions before, and therefore omega gc or the gain crossover frequency, it is this one, decides the rise time in the step response. We will again come to these things when we analyze the low frequency regions, the middle frequency regions and the high frequency regions. So, at the moment it is important for us to observe that if zeta is given right here, then omega gc decides the rise time in the step response, right, because again there is because of this nice correlation over here. Okay. Now, what are the exact specifications, right? So, when the objective is to improve the relative stability of the system, right, then we will specify the requirements directly in terms of the gain margin and the phase margin. Okay. Now, how are they related to transients? Well, the damping ratio was related to the phase margin via this expression, and then a given zeta and omega n, the gain crossover frequency was related via this one. Okay. Now, we go now to the steady state specifications, and the steady state specifications are usually in terms of the error constants, could be either the position error constant, the velocity error constant or the acceleration error constant. Okay. So, we had in the lectures of Bode plots learned how do we get these error constants directly via the Bode plot. We will just try to recollect those again. So, given this Bode plot, what is Kp? And Kp will exist only for a type 0 system, which means that I am actually having a transfer function of this form. So, if I take the limit of limit of gj omega as omega goes to 0, I get that the intersection here is 20 log Kp in decibels, or Kp if I just look at it in terms of absolute numbers. Similarly, I look at a type 1 system to compute the velocity error constant. So, type 1 I have a pole at the origin, and I know that this formula here limit s going to 0 s times gs will give me the value of kV. Now, how do I compute the value of kV from the Bode plot? Well, if I look at very low frequencies, which means omega is very less than 1 or much less than 1, I just ignore these terms. So, for low frequencies this expression would hold, that g of j omega can be approximated simply as kV because of this thing by j omega, and the kV can be obtained by looking at the intersection of the initial slope of this line of this guy with the 0 dB line, or at which point the magnitude of kV by omega, which is essentially this guy, the Bode plot for low frequencies, becomes 1, and the frequency at which this initial line intersects the 0 dB line is actually my kV. We have done this before. Similarly, with the acceleration error constant, I am essentially now looking at a type 2 system, and I know that Ka is given by this formula of limit s tends to 0 s square times Gs. Again, I look at very low frequencies, omega much less than 1, in which case I can approximate my transfer function g of j omega as Ka over j omega square, right. And if I just keep doing all the same exercise, I look at the intersection with the 0 dB line, or in which or in the absolute terms Ka by omega square, which is the magnitude of this, becomes 1. Well, it becomes 1 here exactly at the point where omega is square root of Ka, right, which is from this formula. So, what is Ka? Well, it can just be computed by this formula. It is the square of the frequency at which my initial line intersects the 0 dB line. Okay, now let us talk more in terms of now the performance specifications in the frequency domain. So, the relative stability requirements are in terms of the phase and the gain margin, and steady state are usually again in the same terms of Kp, Kv and Ka, right. Similar to the time domain, again we recollect this in terms of overshoot, the rise time or the settling time. These are now translated via appropriate formulas or relations to specifications on the gain margin and the gain crossover frequency, and steady state specifications remain the same, right. And what we have to be careful here is that the correlations between the time and frequency domain parameters used in this lecture are exact for a second order system, right. So, we started our analysis, all the MP, MR, these were formulas derived only for second order system, and in the time domain we translated this specification in terms of the dominant poles, right, where we wanted the exact plots and the plots with the compensator and the dominant response to be as close to each other as possible, right. So, same thing we could do even in the frequency domain. Okay, now depending on so far we saw relations between how are the phase margin and the gain margin related to the time domain specifications in terms of zeta, omega n, the bandwidth, the resonant frequency and so on. Now, based on what we had argued so far, if I look at the low frequency region, again look at these plots, the low frequency region here, the low frequency regions here, omega being less than 1, or the low frequency regions here, they were deciding, if I call them as region 1, they were deciding the steady state response, right. So, the region 1 will decide how my system behaves at the steady state, right. What is steady state specifications? They are either in terms of Kp or Kv or Ka. Now, look at this region here in terms of the gain crossover frequency, and if we go back a few slides, the gain crossover frequency was related to the transient response of the system. So, this frequency range here, which I call the region 2, will decide the transient behavior of my closed loop system or also the relative stability. Region 3, which is much ahead or much after the region 2 or much after the gain crossover frequency, this indicates in some sense the complexity of the system, what are the extra poles and zeros in the system. And at this region, what we must be careful is that the gain in this region should be attenuated to reduce the effect of noise. So, the design specifications can be categorized essentially into two regions. Region 1, the low frequency taking care of the steady state requirements. Region 2, taking care of the transient response, which is essentially the region slightly to the left and slightly to the right of the gain crossover frequency. And only a specification or only thing which we need to be careful in region 3 is that the gain must be attenuated, right, in order to reduce the effect of noise on the system. Okay. So, how do these things look by construction? So, in the time domain, I know that the lead compensator had a 0 and a pole placed such that alpha was equal to 1, and similarly here I can write down the sinusoidal transfer function. The lead compensator goes exactly the same way, and similarly for the lead lag compensator. I am just writing down the sinusoidal transfer functions here. Here I just call the gain k prime to be just alpha times k, and here to be beta times k, and so on. Okay, so how do we go about doing this? Now we have a nice correlation between the time domain specifications and the frequency domain specifications. We also have nice explanation of the low frequency region corresponding to the steady state requirements, and the mid frequency range around the gain crossover frequency corresponding to the transient specifications, right. So, the first thing as usual we would do is to see in terms of the gain adjustment. Just by adjusting the gain, do I get the appropriate gain margin or the phase margin? And by root locus plots I actually, by the Bode plots I actually know how to compute the gain and the phase margin. So, and once I design or look for an appropriate gain k, and if it does not exist, just by merely adjusting the gain, if my closed loop specifications are not met, then I would use an appropriate compensator. Could be again in terms of a lead compensator and the lag compensator. But as usual, the very simple first step is to just look at a proportional controller or just look at adjusting the gain, right. And then if they are not met, then we look at appropriate regions for the compensation, right. So, in this lecture what we saw is how the time domain and the frequency domain specifications are related to each other, the various regions, how they are categorized in terms of frequency, and in the next lecture we will see exact construction of the lead compensator using Bode plots. Thank you.